Hi, welcome to my talk. Thanks for joining us. My name is Maximilian. I'm working for Eclipse Source, and today I'm going to talk about model validation, diffing, and more with EMF.cloud. So let's dive right into it. What is EMF.cloud? EMF.cloud is a framework for building web-based emphasis, modeling tools or tools. EMF.cloud is not EMF, so it's not the same project, nor does it share the code, but it offers similar concepts. What it does is it provides components that cover frequent use cases for building web-based tools and encapsulates best practices in those components. And last but not least, it also provides architecture blueprints. So if you want to build web-based modeling tools, you can use those architecture blueprints, and those will demonstrate how to use the EMF.cloud components, as well as other components that help you to build those kinds of tools. I said web-based with an emphasis. So what do I mean by web-based? I mean web-based technology. So that is HTML, JavaScript, TypeScript, CSS, SVG, and web-based frameworks like React, Node, and Versify, you name it. Orthogonal aspects to web-based technologies are desktop-based versus browser-based. So you can use web-based technology to build a desktop-based application or a browser-based application. You can have an online or an offline application still built with web-based technology, and same goes for deployment, on-premise, off-premise, cloud-based. Those are not aspects that you choose by choosing web-based technology. That's an independent choice. And in my opinion, web-based modeling tools are the new normal today, even for modeling tools and tools. The reason for that is there's a rich ecosystem of components and tooling from the Eclipse Cloud development projects, as well as from VS Code projects and from the rest of the browser-based world, which is really, really huge. Furthermore, there's a rich ecosystem of committers, contributors, and adopters. On the right-hand side, I've shown all the committers, contributors, adopters of the Eclipse Cloud Dev tools projects. There's a working group that works on those tools. Then there's, of course, the VS Code community and the other communities that build browser-based technologies. There's also some non-functional aspects that are really good about that. You get a modern look and feel, you get lightweight access for your users, there's no installation in that sense, updates are easy to do, and last but not least, you can get developer resources, which is kind of difficult otherwise today. What is the foundation of building those tools? First and foremost, it is Eclipse Theia, which is an extensible cloud IDE platform, and we're going to use that today for our demo. Then there's Eclipse EMF.cloud, which we are talking about today and focusing on that. That's about building web-based modeling tools. We have Eclipse GLSP, which is about web-based diagramming. And last but not least, we have Eclipse Shea and Kubernetes, which is about cloud deployment if you wish to build a cloud-based application. Now to the demo at hand. So what we're going to look at today is one architecture blueprint from the EMF.cloud project called the coffee editor. The purpose of that is to build an example product to model coffee makers for the sake of having a simple example. And we're going to follow a demo path of features that are available in this architecture blueprint. We're going to look at the Workbench with a Workspace. We're going to look at how to build form and tree-based editors, diagrams, textual DSLs. Then we're going to put an emphasis, as the title implies, on comparison and versioning. We're going to look at multi-editor support, validation, which is also an emphasis, and then code generation, coding, and debugging. And we will finally end with a model analysis component. So let's dive right into the first demo, Workbench with Workspace. What I have here is a console, and I'm going to just launch a Theia application, a browser-based Theia application. And this Theia application is containing this coffee editor. What we have here on the left-hand side is an Explorer component that shows the contents of the workspace. I can open up editors. So for example, an editor for this file. Editors can be placed in different places like you are maybe used to from Eclipse. So that's the window management. There's other features of the window management as these different views here. There's handling of menus, and there's a status bar below here. And of course, the workspace, which is underlying the Explorer. So that's basically the functionality that we have here. It all comes from the underlying platform, Eclipse Theia. Windowing, Workspace, menus and status bar, integrated terminal. There's support for LSP, for the language server protocol. So any language that supports LSP can easily be edited within Eclipse Theia. And there's many extensions. One reason why there's so many extensions is also that Eclipse Theia supports VS Code extensions. So it's compatible with VS Code extensions, but there's also Theia specific extensions for debugging, for Git, for the problems view, and many, many more. If we look at the architecture on the right-hand side, Theia runs within the browser or an Electron app if it's a desktop-based application. And there is the Theia front-end component, which makes up the UI. And we have in the backend, the Theia backend. It runs on a node server, and it makes up all the server-side processes. If you run a desktop-based app, that's all co-located on the same machine. Otherwise, browser and Node.js would run on different machines typically. The Theia frontend can be extended with so-called frontend extensions, so they can contribute to the UI, for example, or with backend extensions, so they can contribute new commands, for example. If we look at a very particular example to how to use that structure, we could look at a code generator. Let's assume you have a code generator programmed in Java. It's existing. In order to integrate that with Theia, if you wanted to reuse it, is you will create a CLI based on your code generator. So maybe a main method that accepts arguments, where should the code be generated to and what is it based upon. And you would create a backend contribution, a generator launcher that would just call that code generator when the command to generate code is issued. And then you would have a very small front-end contribution. In the simplest case, a menu contribution that will then trigger that code generation. This is a structure that I'm going to use throughout the talk. So the green components are always off-the-shelf components, unchanged. The yellow components are components that you need to implement yourself to get this kind of functionality. And if only a little bit of configuration or change is required, I have a yellow border around the green component. Form-based editing, first feature of an editor. In many of those many of those modeling applications, you need form-based editing. So I can have a form here for a control unit of the brewing unit within the coffee maker here. And usually this is used for data entry. You can obviously also add other subcomponents here. Also, let's have the dip tray, have a control unit. This is from Intel, has, I don't know, 4 cores and some, that was a clock speed. And the Intel is a vendor and some socket type. So this is typical form-based data entry that you often see in those kinds of tools. Involve components for that. The tree is done with EMF.cloud, with the EMF.cloud tree component, and the forms are done with JSON forms, which is a framework to create declarative forms. If we look at the architecture, we have the Theia frontend, and we have a frontend contribution that contributes this coffee tree editor. So an editor that opens when I double-click this file in the Explorer. In the backend, we have a tree editor connector, which will load the file and provide it to the tree editor. So pretty straightforward. Graphical modeling. We also have a file that makes up a diagram. So we have this diagram here. And this is a diagram editor that I can just create new nodes with. So for example, I could create a node chat here and then connect the two with a flow. And there's all kinds of other tools for the graphical editor. Involve components for graphical modeling. The Graphical Language Server Platform, GLSP. This is like LSP, but for graphical editors. So it means that the VLSP client, so the UI component, is generic. It doesn't depend on your particular DSL. It renders a graphical visualization of your DSL. So in our case, it renders tasks and flows between the tasks as a graphical notation. The GLSP server, on the other hand, is not generic. This is specific to one DSL because it's concerned with mapping the model, in this case, the tasks and flows, to a graphical visualization of nodes and edges. This is based, or is rendered based on the Eclipse Brotty framework. If we look at the architecture and the front end, we have the GLSP editor. This is an off-the-shelf component. The only thing you need to customize is the shape, the SVG-based shapes of your nodes. Then we have the GLSP connector, which is customized to say which files it is responsible for, and it will launch a Coffee GLSP server, which is a custom component and is concerned with modeling, with mapping the model to a graphical visualization. It can do that by making use of the GLSP core framework. Textual modeling, also a very common use case in those kinds of tools. We have a textual DSL here. This describes some probabilities. If I change this to a probability that doesn't make sense, it will tell me that based on the grammar. I can also add some more assertions here. So this is about tasks happening before other tasks. So for example, I could request that the drink activity needs to happen before the new chat activity that we just entered before. Involved components for that, the Theia editor, again, the textual editor, and the Xtext LSP server. If we look at that from an architecture perspective, in the front end, we have the LSP editor, which is an out-of-the-box component. We have the LSP connector, same. And then we have the Xtext LSP server. This component was generated from the Xtext-based grammar, and the only customization it has is a task provider that takes all the tasks or activities from the model that we have created and feeds that into the auto-completion. As we have seen, for example, we had this additional chat activity. Versioning and comparison. So now we have done a bunch of changes, but it's always interesting in those tools to see what the changes were that we have done. So I can just diff that. Note that I don't have a lot of space here. That's why it's very crowded, but we can see that we changed the clock speed of this Qualcomm processor. We added a DIP tray with a control unit. And we can do the same with the graphical visualization. So let me bring that up. Not a lot of space. So right-hand side is the old diagram. The left-hand side is the old diagram. Right-hand side is the new diagram. We can see that we added this edge and a new node. There's also Git integration, so we can see the different files that were changed here. We can also diff the textual file here. So we'll see, okay, it changed in this line, and we added this statement, drink before chat. And we can also go ahead and just stage those changes and commit them to a Git repository, to the underlying Git repository. How is that done? Well, that's done with a alpha component from EMF.cloud, compare. It offers a tree-based compare UI, a GLSP compare UI, and a backend. And we have seen the Theia Git extension in action. We look at the architecture. The Theia Git front end was the one that showed us the files to be staged and committed. Then we had the tree compare UI. And that tree compare UI would, in the background, go to a compare backend that runs in the backend. And it will fetch the responsible file versions from the Theia Git backend and then send those to a compare CLI service. And this compare service will in turn use EMF compare, an existing framework for comparison, to come up with the differences. Same story goes for GLSP compare UI. And GLSP compare UI will then use GLSP as before to render those changes within the diagram using the Coffee GLSP server. Multi-editor support. If you watch carefully, you might have seen that the changes that I did were actually all depending a little bit on each other. So for example, we have seen that I have used this chat task here within the textual DSL after I've added it previously to the Coffee model. And same goes also for the form-based diagram, for the form-based editor and the diagram editor. So if I place those two side by side, and if I find enough space, then we can see that here we have the chat activity within the form-based editor. And within the diagram editor, we also have it here. And this is actually the same element. So if I now go ahead and change that here to complain, it also updates in the other editor. So I have complain here as well, and vice versa. If I change it back, it also changes the diagram. So in fact, those two editors are working on the same model in the background. You can also see that they both became dirty while those edits happened. That's because they work on the same resource set in the background. Involved components, we have the EMF.cloud model server, defines a common API and protocol to deal with multi-editor support. If we look at the architecture, we have the coffee tree editor and its connector as before. But what I'm omitted to say is where does the actual content from the editor come from? And it comes from the model server. So the tree editor connector will connect to the model server. The model server is a component that's off the shelf other than the models that you have within the model server. And then we have the GLSP editor with its stack, so editor, connector, and server. And again, the Coffee GLSP server will now connect to the model server. And finally, the LSP editor with its connector and its LSP server also connects to the model server. And that's the reason why they can synchronize on the changes. So if something changes in the GLSP editor, connector hands it down to the GLSP server, updates the model server, and now the change is sent out to all involved editors, let's say to the tree editor, connector sends it on to the tree editor, and it can update with the new state. Validation. So we also have a validation feature, obviously, so there can be some validation rules on those things. So for example, on this diagram, there's a rule that no node can have two incoming edges. I can see that here now in the problem view. I see those, can even navigate there. So let's say I don't see it now, it gets focused, and I have a cycle that's detected on the diagram here. I can resolve that, for example, by adding a manual task in here, and then just taking the edge and move it over to this new, and my problems are gone. Validation is based on EMF.cloud validation. That can be done, it is able to support different validator extensions. One of them is based on EMF. There can also be custom validators. If we look at that from an architecture perspective, we have the GLSP editor, which with its stack, editor, connector, and server. This time the GLSP server is modified to add validation. It will make use of a validation helper to map those validations back onto the graphical visualization. And it still connects to the model server, which is now modified to also support validation. In our case, EMF-based validation could also be a custom validator that you implement. If we look at that, if something changes in the validation and warning is found, the model server will relay that to the Coffee GLSP server and over the connector back into the GLSP editor. The GLSP editor will then highlight those changes within the editor and also populate the Theia problems view that we have seen. The Theia problems view is part of a Theia markers extension and is just also an out-of-the-box component. On to code generation. So for code generation, I will just generate code from the model. I have a Java code generator and a C++ code generator. We'll first take a look at the Java file. So we have a file for this chat activity that we had here. And now I have a code editor that just does whatever you would expect from such a code editor. It even supports stuff like refactoring, extracting that to a field, into a declaration, call that message. So all the usual stuff that you'd expect. Among them, of course, also to be able to launch that. So I'll debug that, set the breakpoint here. The application breaks at the breakpoint. It even does stuff like showing the local variables and even changing them. So I could change that, continue, and we see the updated message down here. Same goes for the C-based application. I'm going to compile that, and then we're going to head over to the C-based application. We have source code for the chat file here as well. And we can also just launch that with a launch configuration. If we go back to the debugger, there's one for C as well. And that will just launch, and we have a breakpoint here where it holds. And we let that continue. How was that done? So the generator was an Eclipse extent-based generator. We've discussed the design earlier. It's basically only launched via CLI, so very simple to implement. For coding and debugging, it's all out-of-the-box components. So it's not simple, but it's been all done. there is a component, the LSP editor. We've seen that before for the textual DSL. The LSP editor in this case connects to a Java LSP connector and to a Java language server, JDTLS, and that uses JDT in the background to compile the Java code. Debugging, we have a debug UI, and then we have JDB DAP connector, debug adapter protocol, and that connects to the Java debug server. The boxes in blue are the ones that are language specific, but still they're all off the shelf. So nothing that I had to implement to do that. Same goes for C++. There's only slightly different boxes. So this time a C++ LSP connector, ClangD, which is an LSP for C based on Clang, debug UI with a debug adapter protocol connector, and JDB as a debugger. And only the red things on the left-hand side are now the ones that are exchanged, all out-of-the-box components again. Finally, model analysis. So that's a little bit a different feature from what we've seen before. Let me just remove all that. So this configuration file was really about being able to generate an analysis on the tasks. And I'm just going to trigger that, and it opens up a beautiful visualization, what the potential execution paths are and how much of an overall percentage this path would take. Remember, we had 2 independent paths up here. That's why we have this 50% split. That was done, and that's a good example of the other ecosystem with a very popular library from the web community, D3. It allows to do very beautiful visualizations. And then if we look at the architecture perspective, we had an analysis UI. That was the HTML-based frontend that we have seen, a connector that connected to an analysis service, in this case implemented in Kotlin, and it just pulled all the tasks and their flows from the model server to generate this diagram. So in summary, we have seen that web-based tools are really the new normal. There is numerous building blocks available from within the Eclipse ecosystem and outside. If you have an existing tool, reuse and migration are really facilitated, so you can reuse a lot of the old stuff if you make it ready for that. And if you want to take a look at that, there is architecture blueprints available in EMF.cloud. We have looked at one of them today, the Coffee editor, available on GitHub. There's another one, the eCore editor, which is also available on GitHub. If you are building a tool or are thinking about migrating an existing tool, I think the best way to start is really to build a proof of concept based on blueprint to see where the limitations are, where the work is in your particular case. If you have any questions after the Q&A sessions that we weren't able to answer due to time constraints or questions that you don't want to ask in the crowd, feel free to just contact me directly. You can use coffee@eclipsesource.com, and I will personally get back to you. And last but not least, today at 6:15 p.m. CET, we have a BOF Birds of a Feather session, very informal session where everyone can ask their questions about building web-based tool. And that's also an opportunity to get there with your particular case. We will have all our experts on building web-based tools there, and we'll be happy to answer all your questions that might have remained. And with that, thank you very much, and see you in a second in the Q&A session. Hi, welcome again for the Q&A session. I just want to take the opportunity. I will not be able to answer all your questions. There have been many, many questions. Either come to our booth, a link has been posted, or come to the BOF. We will have a lot of time to discuss your questions there, and I will take the remaining time to answer as many questions as I can. One of the questions was, how is EMF and EMF.cloud related? And can I reuse my EMF models with EMF.cloud? Yes, you can. So EMF.cloud is a different project than EMF, but the model server of EMF.cloud can reuse EMF-based models and encapsulates them so that clients don't see that EMF dependency. So you can have editors that don't know about EMF, but still reuse your EMF-based models in the background on the model server. Another question that I had seen is the one about preferred method to build the Xtext extension. Actually, it doesn't matter. You can either use Gradle or Maven. I don't know of any significant difference between them. And last but not least, Do we provide an API to access the model lazily? No, not yet. Very interesting idea. Would be something worth adding. And in fact, we've added a lot of things over time to the model server. So if you're interested in that, I invite you to the BOF to share your ideas. And with that, I would like to close. Thank you very much for hanging in there with all the technical difficulties, and enjoy the conference. Hopefully see you later at the BOF or at the booth.